So the demo is a plane spotter app. And the database behind it is a relational database. I've put it on MySQL. It's basically all the planes registered in the US. The FAA gives out that data, which is great. And then there is a relationship to plane types, obviously. So it's a relational database. Then there is an API app service that basically takes that database data and then exposes a REST API to give back, OK, so these are the planes that I have as results for your search. Right? And we have a front end, Python Flask and Bootstrap based, which basically is just the UI that the user sees. Now, this is all static data, which is a bit boring. There is what is called an ADSB hobbyist network. So the ADSB is what the planes that are airborne are transmitting. And there is a hobbyist network of people that receive that and pump it to a centralized system. And you can get a stream of all the airborne planes, which is actually nice data to tap into. So we have an ADSB data feeder that takes that data feed and then pumps it into a NoSQL Redis database. And so our API server can now mesh that data and can say, for that particular plane in the database, it's airborne or not, and it's at that current position. Right? So that's the application that you will see. So the MySQL database, we manually deployed into vSphere as a VM. Right? It could also have been outside of vSphere, like it could even be a mainframe or whatever this data is, right? But here it's a VM. Then both the Redis database and the API service is deployed as a Kubernetes pod or as a Kubernetes service inside of PKS. So PKS is VMware's and Pivotal's new container distribution, Kubernetes distribution. And I'm using that to deploy those two things. Then the front end is using Cloud Foundry. So we will CF push the front end code into Cloud Foundry. And then finally, the ADSB data feeder is on OpenShift. Now, does it make sense to distribute it that way? You never know. I mean, it might also just reflect the organizational structure of your customer, right? And the technology choices the customer made. Now, in terms of NSX, the whole Cloud Foundry VM-based thing and Kubernetes PKS is one NSXT environment. There is one central entry and exit point, which we call the tier 0 router. So we have a two-tier routing model. And that is like the administratively provisioned router that connects to the physical layer. This is where you would create your BGP, peering, et cetera, et cetera.
So, and you may have already touched on it, but you are still doing the distributed load balancing and stuff like that with this?
Distributed routing, yes.
Okay.
So there is centralized appliances, the edge gateway appliances that you can run on bare metal servers or as a VM. And those are like the entry and exit points to your physical network north-south. And this is where you also would centralize services like load balancer, NAT, etc. Right. But like this routing here between this tier 1 and this tier 1, even if it goes to the tier 0, is a completely distributed routing, will stay in the hypervisors. Right? It will take the shortest path between the hypervisors. We will only go through the appliances if we need stateful services or we need to exit the network.
So it's like the NSX gateway.
Absolutely.
Yeah.
Absolutely. Yes. Well, the routing tiers of NSXT are very different to what we did with NSXV, but essentially you can think of the north-south exit as being this appliance type of thing, right? So those tier 1 routers, that's our tenant routers, they get automatically created when I create a tenancy. So if I create a new Cloud Foundry org, if I create a new Kubernetes namespace, if I create an OpenShift project, it's going to create a tier 1 router and attach it to my tier 0 router. It's going to create an initial first logical switch and assign an IP subnet to it. And depending on if I want to use NAT or no NAT, it's going to assign a SNAT IP to that specific tenancy, to that specific namespace or that CF org. Right? And so now if the traffic comes out of that plane spotter namespace, if it's natted, it will use a specific SNAT IP that I can allow in my backend database system, in my ACLs, etc. Right? But I can also decide to say, no, I don't want to have NAT because, I don't know, my application doesn't support it or whatever. Then we can just annotate the namespace and say, don't do NAT for that. And then basically the whole subnet will be routed out. And then you would need something like even static routing or a BGP to announce your newly popping up subnet. Right? Now for those here, we have our load balancer tiers for both Kubernetes. The PCF load balancer is currently still manual, but we are working on that. But that's also going to pop up automatically, get automatically a virtual IP, et cetera, et cetera. Now in my lab, I have the OpenShift part on another NSXT environment, but that's just like my lab setup, right? It might, again, reflect your organizational structure or whatever. OK, so let's go through the demo. I'll have to sit for that. OK, so the first thing I want to show you, wait. So the first thing I want to show you is the database. So here in my vSphere environment, I have one VM here. That's the PlaneSpotter MySQL. And it's connected to a logical switch called database VM LS, so logical switch. I will have to log in here. If I look at my switches in NSXT, you will see that I have a database VM LS here. And if I look into it, I have related ports. And one of the ports is my port for the VM here, PlaneSpotter MySQL. And I have to size that a bit so that you see it. Down here, we have the VIF. And I get the details like the VM name, etc. Right? So NSX has a full visibility of the whole vSphere layer. And we also collect that in our inventory. So here we see all the virtual machines, and here's my PlaneSpotter MySQL VM. And I tagged it with a specific sec group. And so that tag could also come from an automated system. So if you would use VRA or something like that to automate your deployment, you can also automatically tag your VMs. That then is used by a group. And here I'm using a manually created group. That's why I call it an admin group. And here I define my membership criteria, and I say if the tag equals MySQL, anything that is MySQL in the sec group, then make that logical port or that VM a part of that group. So anytime I create a new MySQL database, it would pop up here in the group. And as you will see later, we use that in the Firewall Rules set to say, for the API server, you are allowed to access the database tier.
Now, do I get the same visibility when I'm looking at KVM as well?
Yes.
OK.
OK, so let's go back to switching. So down here, you see a number of existing logical switches for default, kube-public, et cetera. What is that? So that is coming from Kubernetes. That's the PKS side. So if I look at my oh, wait, I have to move that over. Yeah. So if I look at my namespaces here, there is already a Redis namespace, there is a kube-public namespace, etc. And we can find it here. So here's our Redis logical switch. And it is connected to my tier 1 logical router. And it has one pod, so one workload in it. So let's have a look at the definition of that Redis. So here's how you define the whole thing. First of all, I have created a namespace called Redis, and I annotated it with no SNAT true, which means I don't want to use SNAT for that. That could have two reasons. The first reason could be I really want to see the actual IP. In my case, I just don't want to waste an SNAT IP because I have a load balancer below, and I don't expect my Redis database to talk to the outside world, so I don't need to waste an SNAT IP, right? So here's my pod, so my container that I'm starting. And down here is our service. That's a Kubernetes service, and it has the type load balancer. So this is something that is also especially in our integration because like usually there are some clouds like Google Cloud that support this service type load balancer, but for SDN integrations, there were not many. And like for us, it means load balancer is a hint to NCP, to our integration. Hey, we want to have a layer 4 load balancer for that. Not a layer 7, but a layer 4.
It for that, right?
Yep. Sorry?
Yep. And it automatically goes out and configures the load balancer.
Correct. So let's first have a look at what we see here. So that's our Redis namespace content. And one of the things is the external IP here for my service, which comes out of the box as soon as I create a load balancer type, right? So let's have a look at the service in detail. You see, I only have one pod in here. That's the pod that you saw. And I have my external IP. So before we look at the load balancer, let's have a look at the pod itself. And here you see the same concept. We get all the metadata from Kubernetes, which is, let me go back here, the labels that we have here, plus things like what project it is in, etc. So it is in the project Redis. And I had labels tier backend and app Redis server, right? And again, I'm matching on those with my API server here. Sorry, not my API server with Redis. And in this case, it's not a virtual machine, but a logical port. And the membership criteria is just taking those tags that we see from Kubernetes. Okay?
So actually, a developer don't need actually access to the VM. If he tags it right on his container view, it's automatically feed it.
Absolutely. That's the most important thing in our integration. We don't want to stand in the way of the developer. For us, it would be like a complete fail if we would say we have to pre-create something before the application can be deployed, right? Because that is exactly what people don't want to have. They don't want to hinder productivity by having like first something to have been pre-created, right?
If you see a developer run around with a spreadsheet that says you need to put all your applications on these nodes, you're in trouble.
Yeah.
I've seen it.
So let's have a look at the load balancer here. And there we look at the VIPs. And there is one VIP that is already there for Redis. And this is the IP address it got. So that's what we saw before. And it uses one specific server pool, which is my Redis server pool. And if you look at the pool members, this is exactly the IP address of the endpoints of the pod, right? And that got automatically created. It was not there before. I just decided to not make it create dynamically, but have it pre-configured here. But for this part here, which is the API server, you will see that everything will be created dynamically. So here I have another namespace, which is called PlaneSpotter. In this case, there is no annotation because I want to have external access. It needs to access the internet. It needs to access certain things. So I will assign an SNAT IP. Same thing here, I have my labels so that I can identify it in NS groups. And that is the most important part here, which is the Ingress. So that's a layer 7 load balancing definition in Kubernetes, whereas the service before was a layer 4 definition.
You had an app which is kind of running like layer 4, and another app, microservice, which is kind of HTTP.
Yeah, so Redis is not an HTTP protocol.
Exactly.
Right? It has its own protocol, its own TCP port.
Yeah.
So I can't load balance with a layer 7 load balancer. But of course, for my API server, that's a REST interface, so I'm load balancing on layer 7. Right? So I'm matching the host name for that particular service, and I'm sending it to the PlaneSpotter service. So let's quickly review what we have right now in terms of switches in NSX. And you see down here, we have default, kubepublic, kubesystem, PKS infrastructure, and Redis. So we don't have any PlaneSpotter yet. So I'll create now that from my spec, and it will create my PlaneSpotter app. It's already running, right? And so if I refresh here, I get my new logical switch, right? I also got my new logical router. Let's have a look at the logical router here. PlaneSpotter. And that logical router got, obviously, an IP address on its port. Where did this IP address come from? It came from our internal IPAM. So here I have my IP block, which is a big pool of IPs. And I carve out individual subnet for each of those logical switches that get created. If I run out of IP addresses, I will create an additional logical switch and an additional subnet and assign that to my tier 1 uplink, downlink.
Do you support like Infobox and things like that yet?
Not yet.
Not yet. But eventually.
Yes.
Okay.
I mean, we get that asked pretty often.
Yeah.
Right.
Yeah.
But at least this is, yeah.
So today, the idea is you kind of, every time you set up this cloud infrastructure, you get one big block, and then you register with NSX. But we do get the ask to kind of integrate this with Infobox so that, getting the next block is like an automated. So we don't have that yet, but we hear that often.
So let's have a look at the layer 7 part here at the Ingress. So we're matching on that host name, and we're sending it to that service. And that was translated to a virtual server that is already there. So for each of the clusters, we create a layer 7 virtual IP for HTTP and HTTPS as soon as the integration starts up. But there is no server pool yet. But as soon as I create my ingress, or I define an ingress, we'll add an LB rule here in that specific VIP. Okay, I'm just moving it over. And here, oh, what is that? So PlaneSpotter API, PKS eve.local, that was my host name, and I'm sending that to a specific pool that was auto-created. So if we go over to the server pool, there's a new one here, and the pool members, in this case, is my PlaneSpotter pod, so my Kubernetes workload.
Can I ask one more question?
Of course.
DHCP. So are you guys looking at just plugin based, or are you going to look at being like a relay where I can send to maybe ISC DHCP or
in the
any flavor of DHCP?
The container world doesn't really speak DHCP. So the way things are done is the CNI interface, which runs on the node where the containers get started, is taking that IP and is configuring it into that IP namespace. So in the Linux IP namespace, had nothing to do with.
More or less like saying when I create a provider, that I say I want to use one of these providers, or I want to also be my own relay, which basically on the host I would just be a relay, right?
Like if I would think of it creatively, I would rather have like an DHCP proxy that just like sends DHCP requests to a DHCP server and reserves it, and then basically assigns that to the container that still gets manually provisioned, because we don't, else the containers would need to have a DHCP client in it, which is not a good idea, right?
Right.
Yeah.
Okay.
Okay. So going on, or moving on, now Cloud Foundry. So we have our API server. Let's look at the Cloud Foundry side. Cloud Foundry doesn't have namespaces, it has orgs. And right now we only have the system org. And so if we look at our logical switches, we'll find one which is called PCF Foundation 1 System 0, which is the first logical switch for the system org. All right? So what I'll do now is I'll create a new org. I also have to create a new space. So Cloud Foundry has a 2-level of tenancy. And then I say, OK, target that org in space. Now I go into my app, and I push it. You will see here, if I refresh, there will be no new logical switch, because the logical switches in Cloud Foundry we create once we see the first container. So that is a bit different. Here we have creating container. What the container that you see created here, OK, now we will have our PlaneSpotter org switch. The container that gets created here is a staging container. So it basically right now installs Python. It packages up my app, and it creates the container for me, because it's a pass, it's not a cast, right? In Kubernetes before, what you saw is I have a container image which is on Docker Hub, and I just say, hey, run that container for me. Here I tell Cloud Foundry, here's my code, package it for me, and then it will create a container. So it takes a little while. Here right now it's like pip installing all sets of stuff. And then once that is done, we'll go back here and refresh. Right now it still doesn't have a name, it only has an ID. But here we already see destroying container, successfully destroyed container. So the build container is gone, and the actual workload is now there. And same here, now we're in the running phase. We have the org name, we have all sets of IDs that we can match on. Okay? So now, yeah, our application is at the state where I can actually access something. So let's do that. So here's PlaneSpotter. Oh, and the size is kind of broken. OK, now it's better. So let's have a look at the aircraft registry, and let's look for American Airlines. So now I see all the planes that American Airlines registered in the US. I can look at an individual one, which is this one. There is no picture for that one. Okay, that's a boring one. Next one. Okay, still no picture for that one. Okay, but you get the point, right? So I can search for any plane. Like since we have Germans here, there is one thing that connects us, and I want to show you that. Oop, 747 SP. That's one of my favorite planes in the registry. This one, it's an old 747 that the German DLR, so the Lufthansa, so the space agency of Germany, and NASA work together, and it's a telescope plane. So it has a giant telescope in the plane itself, and it opens up that lid here in the back at 12 kilometers high to watch the stars.
That's cool.
Yeah. So hey, Germans and Americans do great stuff together. Okay, so now if I look back at here, American Airlines again, then you see no airborne planes. So it can't be that American Airlines has all their planes grounded. Obviously, we didn't deploy the ADSB feed yet. So in this case, we'll use a new context for kubectl, which is my Openshift Origin. And I look at my projects in Openshift. And yeah, come on. While it's doing that. So here, same thing. It looks pretty similar. It's just different projects. And if we look at NSX, you'll get the similarity. We have logical switches for those networks or for those projects. Right? So we'll just deploy it. Yeah, same thing. It's creating a project instead of a namespace, but the rest is pretty much similar. So now refreshing the switches, we now have the ADSB sync switch with a logical port. And here, what I didn't show you yet is the monitor part, right? So we have obviously counters for our, and I can't refresh for some reason. That's likely a, okay, I can't refresh right now, but you get the point. We have counters for all our containers and pods, just as if it would be VMs. And here we also have things like span. So we can create a span session, a port mirroring session, and send the traffic of that individual pod to some traffic analysis station for troubleshooting, right? So all the network tools that you are used from like a VM form factor, we also have for containers. Okay, so let's have a look at the American Airlines again. Now we should have airborne planes in the air. American Airlines has a lot of planes in the air. So look at that one. Still no picture of that one, but we can have a look, and it's somewhere near Las Vegas. So where is it actually flying to? From JFK to Los Angeles.
So that's the current live location of the flight?
Yes.
Pretty cool.
Okay, so now my application runs perfectly. Let's break it. So I promised you we'll look at the firewall rules. So here I have an admin section where I have configured my firewall rules, and since that is really, so that is a bit better now. Okay. So here I'm allowing from the Go routers to the web front end, etc. I'm not going to go through all of this, but this one here is my rule coming from the API server, logical port. So that's the group collecting the PlaneSpotter API server. To the MySQL database running on that VM. So here's my virtual machine. Okay. So, and right now it's allowing MySQL on port 3306. So I am now the bad guy that did a massive mistake and brought down the whole application. If I now go to my registry again, yeah, it already takes too long, and yeah, it went wrong. Let's have a look at the app health.
Apropos.
Yeah, and we see, okay, database connectivity failure. So somebody messed up with my database connection, right?
That ain't the Hudson.
So how would I troubleshoot that? I would go as a like SRE for that application, I would go to the traceflow tool in NSXT. I would say, okay, from that specific logical port, and I know it's something with the app service. So I'm going to select my app server. Where is it? Like this is difficult to find when, yeah, here, plain spotter app. To my plain spotter MySQL. I know that it communicates over MySQL, obviously, so I'll just take some ephemeral port here, and 3306, and I'll send a artificial SYN over to the destination logical port. So let's start the trace, and now NSX will go through all the elements that NSX knows about in the path from that logical port to that logical port, and will give me a nice report here. So it knows that it went through that logical port, it went through that virtual router, etc., and it maps that out, right? It also shows me, hey, your tunnels between your two hypervisors are healthy, right? They would show up as red if the tunnels are down. We would even show physical switches that our hypervisors are connected to. So if we get them through LLDP, we would show them here, right?
So do you have is the API exposed to also automate that?
Yeah. Absolutely, you could build your own tooling for it.
Okay.
It's like everything that we do is greatly documented in the API spec. So there is the API documentation here online on the system, and we also have a Swagger spec, so an open API spec of the whole API on the system. You can just download it, and then you get all the stuff, right? So here we know, okay, it's dropped by firewall rule 281, so we'll just repair our application. It's indeed where was it? 281. So repairing that. And to prove the point, we'll refresh that app health, and yeah, database is back. And now I also want to show you the traceflow result when things are good, because there you really see on the side all the steps with all the details, which is pretty nice.
So this is NSX simulating application traffic on behalf of the pods.
So now we see it's received at the logical router port, etc., and then it flips over on the left side where you see, okay, this is actually what path was taken through the system.
So can you touch on how external services would communicate into, say, the service mesh? I guess is where I'm going with that. Like, as far as like load balancing, if I wanted to programmatically.
Yeah. So today, I mean, there is a future view of what we will do in the future. That is certainly for another time. But what we can do today is Service Mesh has those Ingress proxies, the envoys. And they actually need a layer 4 load balancer.
Yeah.
And so the service type load balancer that you just saw will serve exactly the purpose of doing Ingress load balancing to all those envoys.
So I can route it based on suffix or something like that, DNS suffix or.
No, for like the Ingress to envoy.
I think I'll take a step back. The way to think about it, right, is NSX is basically providing all of the services required for that microservice, right? So basically, essentially what it's doing is, let's take a step back and see what actually Yves demonstrated. Yves demonstrated deploying a microservice and accessing that microservice from an external environment. So what has happened there is that for that microservice to deploy, we did IPAM, we did IP address per container or pod in this case of Kubernetes. We connected it to a network. We kind of deployed one namespace with like no SNAT and one namespace with SNAT, which means that for the SNAT namespace, we advertised a BGP, a single IP into the network, right? And how did this whole stuff happen? We also created load balancing. So what we did is we basically created like a virtual IP on the fly and configured the backend pods as the backend of a load balancer, right? Yep. So typically all these systems are working in a fashion where you have wildcard DNS to point to kind of say star.appcloud.something. So it's attracting the traffic. The moment the traffic comes in, NSX is a layer 7 load balancer. Right. So it saw that the application has a specific URL, and we know at that point of time what IP address that backend pod is. So the backend pod could have like an IP that's natted at the edge of the NSX, or it could be completely routed.
But what if I have multiple services, right? They use the same ports and things like that.
Well, service mesh itself is not only a layer 7 concept,
DNS,
right?
things
So that's why they want the layer 4 load balancer in front of all those ingress envoys, right? But there is also what is called an egress service for service mesh. And there they also profit from the fact that we know the source IP the traffic will come from. So we add a lot of value today already in the service mesh environment.
No, I'm not super clean. Exactly. So that is the key point.
That is a different story. Yeah.
Yeah.
You only need an envoy if you're inside of Google or Amazon, and they're not doing the load balancing to find a function, right?
And once you put a load balancer in way, then you can use it as a visibility tool.
Right.
Well, guess what NSX does? Gives you the visibility that you need. The purpose of a service proxy is to give you visibility, because you have to have packets going through it, because you get no network visibility in the cloud, so you run it through. Once you've got a service proxy, what do? Oh, it's just Nginx. So I can start to do load balancing, I can start to do app rewrites. If it's if I put certificates on there, I can do decode and blah, 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 and I can do logging, I can do whatever. But it all comes down to, I need some sort of visibility in the public cloud. When you've got NSX, you do all that in the vSwitch or in the NSX agent, be it T or V. Yeah?
T.
Yeah, or V. Yeah.
We'll take it offline.
Yeah. So I think I think one aspect that was not super clear is NSX assigns a unique IP address to every pod, and that IP address is visible throughout the life of the network. Right? So which means that if you had a Redis, like an app, like an in-memory database, and like an app that is kind of trying to query data from Redis, it actually sees the Redis IP, right? All of your physical firewalls see the Redis's IP, right? So that is the fundamental difference. You need something like service mesh if you're trying to do something completely on top without having access to the underlying infrastructure. NSX is building a network with bringing the containers directly to the data center network.
Key, because this is what AWS did. They attached one IP address, pointed it at a service, and this is not something we've historically been able to do.
Correct.
It's service steering.
Sorry?
It's service steering.
Even at a more fundamental level, the idea is that in AWS, you can just get a public IP address from a pool, and then you attach it to something. We can't do that in a modern data center without having to,
Correct.
Get a mandate from God to make that sort of change go through. And he just did it here while you were watching.
Yeah.
Right? I think that's more what the demo is sort of shouting out to me.
So what AWS did 3 months ago was the ability to plug a container directly into a VPC network. So what NSX did exactly was the same. You have a data center network, we plugged the container, irrespective of what platform it was, whether it was from Kubernetes or OpenShift or Cloud Foundry, we plugged it directly into the data center network. At which point, you can use all of your load balancing that you have, all of your physical firewalls that you have for that endpoint.
The devil's in the details, of course, like any good service, because they all work slightly, but that's functionally it.
The key point is we did all of this without touching the NSX. Directly, when the developer program.
They were doing it all from Kubernetes.
Yeah, so let's repeat that because you didn't have a mic. So you can repeat it yourself. There's a mic coming to you.
So the key point is we did all of the above without touching the tool. So when the developer pushed the app, automatically all this happened in the backend. So nobody had to actually plumb it.
I think to see the consequence of what that is, right? This is infrastructure teams enabling greater developer velocity, which is what organizations are really looking for, right? Infrastructure teams have been seen as a hindrance, but this infrastructure teams actually enabling greater developer velocity. So developers are getting a Kubernetes native API or an application platform native API, but infrastructure teams are enforcing policy, managing that infrastructure, monitoring the infrastructure. So this is really enabling both these people to go ahead, right? Networking infrastructure teams need to monitor it, they're answerable for it, developer teams need to go fast. This is really enabling both of them to go fast, right? And we go from where we're seen as a hindrance to now actually enabling greater developer velocity. That's why this is seen as compelling.
Good stuff.
Okay.
That's your summary slide. Or we already did that. We did that right now, right?
Yeah, I think we did that, right? Pretty much did that. So
we did it verbally.
That's right.
Yeah. In real life.
Yep. So the difference between seeing it last April and now is now this is all GA software with customers deploying it, actively deploying it.
Right.
Yep. All right.
Which is pretty cool. And the NSXT is the key here because that's the tool that came to the market that lets us reach into Linux.
Yep. Cool. Thank
The
you.
T stands for transformers, by the way.
Oh,
Would you say that it has something that more than meets the eye?
I'm sure somebody would like you to think that.
Right. Thank you.
Thank you.